course, it's published on GitHub. It's cross-platform, so we have continuous integration to ensure that it always works on Linux, OS X, Windows, even Windows XP, actually. So why a just-in-time compiler? So as you all have noticed, pure Python is slow at number crunching. If you write a loop and compute various operations on one element at a time on say, a Numpy array, you'll notice that the numbers are very bad compared to what you would expect from C, Fortran, C++. So the next thing you can think about is, well, I use Numpy because Numpy has linear algebra. Numpy has specialized loops for various kind of matrix operations or vector operations. So this is good as long as your problem can be expressed purely in terms of linear algebra. But those are only the well-behaved problems, and there are a lot of problems which are not that well-behaved. So the first problem is that array operations are memory heavy. So for example, if you apply a string of different operations on an array, Numpy will do one operation at a time on the full array. So if your array doesn't fit in the CPU caches, then you have some cache thrashing, and the cache efficiency of the CPU is decreasing, and you observe some suboptimal behavior. The other problem is that many algorithms are not really nicely expressible in terms of linear algebra. So for example, they have irregular data access. They have some per element branching. You can have a number of iterations per element in your array. Perhaps you have some backtracking where you are going back on your array based on some element and some commutation result. So you really want C-like speed, but you don't want to write C or Fortran or any kind of low-level language, even though you may end up write some kind of Fortran in Python. But so this is why you would want a compiler to have fast numerical code from your Python code. And so why a just-in-time compiler? Well, one thing is that it is fit for interactive use. So say you like to use an IPython notebook to run experiments. Well, Numba, since it doesn't force you to jump out of interactive session and type a compiler command, you can JIT your function from the IPython notebook. And so you can experiment on the fly without having to disrupt your workflow. So just a quick example. So this is good old Mandelbrot. So everyone knows Mandelbrot, so it's quite easy to understand. You know that Mandelbrot exhibits this pattern of having some per element branching, because when you compute a point in the Mandelbrot set, you can exit early from the loop. So the pure Python version is very slow. Your first hunch is to write a Numpy array version, and it's not very fast because you cannot benefit using Numpy array operations from the fact that that there is some early branching or some early exit on a lot of points. So using Numpy array-wide operations, you can still have code that is, on this example, 30 times as fast. Then you rewrite the loop using Numba, and you get, on your CPU, you get a 120 times speed up, which is more like the speed of C or Fortran. And if you use the specialized decorator in Numba to run the code on the GPU, then depending on your GPU, on a fast one, you can get to 2000 speed up. So 2000 times speed up means it's perhaps 100 times, 10 times faster than on the CPU. So why LLVM? Well, LLVM, the nice thing is that it's a mature library which has been developed since the early 2000s. First in academia and then supported by the industry. So C-Lang, which is the compiler derived from LLVM, is the default compiler on OS X, I think. Perhaps on the BSDs too. It's multi-platform. There are many people working on it, so there are a wide range of integrated optimizations, all kinds of optimizations you may expect to find in a compiler, actually. So it allows us, Numba developers, to focus on Python and everything which is specific to Python, as opposed to the low-level optimizations, register allocation, and so on. So the kind of optimizations that LLVM has, they are the quite typical compiler optimizations. So especially of interest in our case is inlining, loop unlowing, SIMD vectorization. So in some cases, when you compile a loop with Numba, LLVM is able to actually vectorize and emit SIMD instructions to parallelize it. So here is an example of a crazy optimization by LLVM. It's something that I was surprised to observe. So it's a bit silly, but if you write the naive formula for the arithmetic series in Python and compile it using Numba, then you really have a constant time function, actually, because LLVM, for some reason, is able to extract that this is the arithmetic series, and so it removes the loop and just replaces it with the final formula. So when you look at the assembler output, which Numba allows you to do, you see the 4 assembler instructions, which are circled in red. They are just the expression of the mathematical formula, n times n minus 1 over 2. So in terms of countability, so it runs on CPython from 2.6 to 3.5, actually. So it can run side by side with regular Python code, which means since we are using the same runtime that most people use, which is CPython and not PyPy or something else, you can have arbitrarily complex or weird code around your Numba compiled functions, and Numba doesn't care. So it can run side by side, and with all the third-party extensions you might rely on, and there are many of them in the scientific computation ecosystem, so not only NumPy, but all kinds of wrappers around weird Fortran libraries. So it's opt-in. So opt-in means when you want to compile a function using Numba, you apply a decorator to it. That means it only accelerates the functions you ask it to accelerate. So this has a nice property, is that it allows us to relax the semantics of Python code. So I'll detail a bit the semantic changes. And while it relaxes the semantics, the code surrounding your Numba functions can still be arbitrarily complex Python code, and doesn't have to be affected by its semantic changes. So I said it's specialized, so tailored for number crunching, NumPy arrays. We're trying to expand, of course, that scope. It has begun as a purely specialized compiler to accelerate NumPy-based loops. We are progressively trying to expand the range of things that we support because there's some demand for it. So there are multiple targets. As I've alluded to, there is a server CPU target, of course. We officially support x86 and x64, but LLVM is multi-platform, so ideally we can support many other architectures. It's just that we don't, for now, we don't run any continuous integration on them. We have a CUDA target for the NVIDIA GPUs with a limited feature set, which is due to the fact that some features in Numba need some C support code, which hasn't been ported for CUDA. And of course, there's potential support for other architectures. So there may be support one day for HSA, which is AMD's architecture to ship code on both the GPU and the CPU. It means a heterogeneous system architecture. We will probably want to have support one day for ARM processors, since they are quite fashionable. So, Numba architecture. So it's a straightforward function-based JIT, which means that it takes one function at a time, it compiles it based on some type information. It doesn't try to do anything fancy like, for example, PyPy does. PyPy is a tracing-based JIT, so it tries to extract some hot loops from your code and records the execution traces and compiles it. The compilation pipeline starts from Python bytecode and goes to LLVM IR. So LLVM IR, intermediate representation, is the information we give LLVM. It's a kind of high-level assembler, and we give that to LLVM, and LLVM compiles it to native code. So we really concentrate on the pipeline from Python bytecode to LLVM IR. As I said, the low-level optimizations, such as inlining and so on, are delegated to LLVM, so we still try, of course, to emit code that is nice and well-behaved enough so that LLVM can apply those optimizations. So there is some cooperation with the compiler. And in the end, we also compile Python-facing wrappers because we first compile a native, low-level native function, which represents your Python function. And then we have to compile a wrapper because we have to expose it to CPython so that you can call it with Python types. So what does the architecture look like in the inside? So it starts with a Python bytecode. There is a first stage of bytecode analysis, which produces two kinds of information. One is the control flow graph, and the other is the data flow graph. So it's pretty standard compiler technique. The control flow graph extracts the basic block in the bytecode, and it allows us to do all kinds of analysis. So one analysis is loop detection. With the other piece of analysis, which is the data flow graph, we can also extract other information such as the liveness of variables. So we are able to extract which variables are live at which point. Once we have that information, we can run some stage called bytecode interpretation, which produces the Numba IR. So the Numba intermediate representation is a rather high level and abstract representation, which is used internally because we don't want to deal with bytecode anymore at that point. So the Numba IR basically is untyped, it's really very abstract. But then we have a type inference phase. Because if you want to produce fast native code, you want to know which types you are acting on. For example, you have an addition, you want to know if it's an addition between two ints or two floats. So we run type inference starting from the function entry point. We know which types the function is called with, so we propagate the type information inside the function. And hopefully we get a wholly typed Numba IR at this point. And then through a last stage, which is called lowering. So the word lowering comes from LLVM jargon. I think it's not necessarily a standard word, but that part takes the rather high level and abstract Numba IR and produces some LLVM IR out of it. So as an escape hatch, if the type inference isn't entirely successful, it jumps into another mode, which is called object mode, which basically does not produce any optimization at all. But the object mode has one property, is that it can still extract a loop from the function and recompile that loop in native mode. So say if you have some high-level operations outside of a loop, then Numba won't be able to optimize those high-level operations, but it will extract the loop and compile the loop in fast code. So this is more of an implementation detail Numba. And I don't know if it's something we're going to keep, but it's an interesting property. So Numba specializations, if you look at that drawing, the lowering part, it really looks like a small part like the other ones, but it's really the one that takes the most code roughly, because lowering means we are able to generate specific code for each kind of operation. So we are able to emit code for example, integer addition, float addition, but for arbitrary kinds of complex code. So if someone is calling a function in the random module, which we support, then it generates some code for our Mersenne twister implementation and the distribution that the user has chosen. And so we have implemented support for various specific libraries. So most libraries we have implemented support for are, of course, the mathematical libraries, math, cmath, random, also the NumPy equivalent, such as numpy.random. And of course, we're looking to improve that in the future. So what do we support? We support, so on the syntax side, we support the basic control flow operations, of course, while loops, if, etc. We support raising exceptions. We don't support catching them. So basically, you're raising an exception from a compiled Numba function, and you're catching it from your Python code. We support calling other compile functions with various call conventions, named and default arguments, and so on. We support generators. This is very new. It's actually in the next release, which will be out in, I think, perhaps 1 week. So you can write generators in Numba. Actually, you can write them in Python and compile them with Numba, which has two effects. You can either use the generator from pure Python code, or you can use the generator from another Numba compiled function. And if you use it from a Numba compiled function, then LLVM hopefully is able to inline all of it inside the calling function, so it can make for some rather fast code. So what we don't support as for syntax, as I said, we don't support catch-in exceptions. A consequence of that is that we don't support the context manager either. We don't support comprehensions generally, either list, sect, dict, or generator comprehensions. And we don't support the new yield from syntax. So apart from syntax, we support a bunch of built-in types. So the number-related built-in types, of course. Integer, Boolean, float, complex. We support tuples and known because they are useful even in mathematical code. We have some support for buffer objects which expose the buffer protocol. The buffer protocol is really a way in CPython of exposing objects which are backed by a bunch of bytes, memory area. So this means bytes, byte array, memory view, and other objects of that kind. So for example, array.array, we support it. This probably means we support mmap files too, because mmap files are able to export a buffer. We support a small range of built-in functions. So there's one, abs, enumerate, and so on. So that's pretty much it for the built-in support. Oh yes, the modules. So in the standard library, we support, so as I said, CMath, math, random. We support C-types and CFFI. So CFFI is, you may not know, is a third-party alternative to C-types. What we support in C-types and CFFI is simply that if you declare a function extracted from a library in C-types, for example, you are exposing the sign function for the math library, when you can call it natively from a Numba function. And of course, we support Numpy. Well, we support parts of it because Numpy is huge. So what do we support in Numpy? We support, of course, all kinds of arrays, so either scalar or structured. So structured arrays are arrays where each element is actually a composite element with different fields and different types. The only thing we don't support as far as arrays are concerned is arrays containing Python objects, which means pointers to Python objects at the low level. So we support basic operations such as iterating, indexing, slicing, which support various kinds of iterators. For example, the .flat iterator, the nd enumerate iterator. We support the reduction functions and methods on arrays. So argmax, max, prod, sum, I think there's var, std. There are perhaps 7, 8 of them, I don't know. Yeah, I'll mention that we mentioned scalar types and values, and we have support for the little-known datetime 64 and time delta 64. So datetime 64 and time delta 64 are two specialized types in Numpy, which represent datetimes and time delta in a very low-level way. So basically, it's just a 8-byte integer, 64-bit integer, with a unit. So the unit can be milliseconds, second, etc. So they don't have a lot of semantics attached to them, but they can be quite useful if you want fast computations of this kind of data. So we support arrays of datetimes and time deltas, and we support them individually too. So other limitations that recursion is not yet supported, so this is something we plan to look into because it's quite useful. We can't compile classes. So, well, one reason is that we don't know exactly what it will mean to compile classes. Do we want to infer the structure by ourselves? Or do we want to have the user declare all the fields and their types? We don't know yet, so it's an open question. We can't yet allocate array data from functions, which is a bit annoying limitation. But this is something we plan to lift in the coming months, I think. Well, one limitation is that for Numba to be able to compile a function, type inference must be able to determine all types, which means your code must be well behaved enough. If your code has very dynamic behavior, and for example, if a variable can be either a string or an integer or a dictionary, then it won't work. So our semantic changes from Python. So as I mentioned, since you are declaring which functions you compile, we can choose to change semantics in those functions. So the main semantic change is that we use fixed size integers. So usually Numba will infer that you want the machine size integer. So for example, 32 or 64 bits. We freeze the global and outer variables. Which means really that the value is frozen at compile time, and you can, of course, modify those global variables from pure Python code, but Numba won't see the modification. We don't allow frame introspection inside the JIT compiled functions. This is because we don't have execution frames at all. So tracebacks, if you have a traceback, an exception raised inside a Numba function, the Numba function won't appear on the traceback. So the traceback part is probably something we're going to improve at some point. And the other consequence of that limitation is that we don't support debugging inside the Numba compiled functions. As with Python, you can import PDB and call set trace. So how to use it? Using Numba is very simple. You have an @JIT decorator. So you tag @JIT to your function to designate it for JIT compilation. There are two main modes of invocation. The first one is that you don't add any parameters to your JIT decorator. So in this mode, Numba will operate in lazy compilation mode. This means really that Numba will wait for the first call to a function. We'll see with which kinds of arguments the function is called, and we'll infer the typing from that first call to a function. So this is really very, very command in mode because it's easier than declaring everything by hand. But you can also choose to specialize by hand. So you can pass a signature here in string form. So it's a kind of mini language you have to learn about if you want to use that feature. And this means you can also specialize your function for types which will not have been inferred by Numba. The main use case I can think of is choosing to use a single precision floating point, because by default Numba will use double precision. So another feature with the JIT decorator is that you can release the global interpreter lock inside the function. So the global interpreter lock in CPython is a mechanism by which only one Python thread can execute at a time. So it's well-known limitation to scalability with CPython. Releasing the GIL in standard Python code is really not possible because of all kinds of internal coherency issues in the interpreter. But you can release the GIL in a Numba compiled function because Numba really doesn't call any CPython API once it's inside your function. So you just tag nogil equal true in your JIT call, and Numba will release the GIL for you. So you get multi-core parallelism. So you can, for example, schedule that function on 4 threads and get 4 times the performance. But of course, you get no protection from race conditions. When you use that option, you are basically in the same situation as a C or C++ developer who runs multiple threads on the same time. So you have to think about data access and so on. So as a tip, there's a nice API in the standard library in Python 3 called concurrent.futures, which has a thread pool executor which will automatically dispatch whatever you want, actually, a function call to different threads. So you choose your number of threads in the pool, and it will dispatch your function calls to those threads, and you can wait on the result. So another way using Numba is the vectorized decorator. So what the vectorized decorator does is allow you to create new universal functions. So what is a Numpy universal function? It's a function which operates element-wise on an array. What this brings is that Numpy, so there are many of them bundled with Numpy, such as np.add, np.molt, and so on. They are the same as the operators. So when you use the plus operator between two arrays, it really calls numpy.add under the hood. So it allows you to apply an element-wise operation on entire arrays, and you only in your ufunc you only define the element-wise operation. It also it enables the automatic broadcasting feature of Numpy. So you say, for example, if you add a scalar with a Numpy array, actually the scalar will be added to every element in the Numpy array. That's what it is called broadcasting, and broadcasting can be much more complex than that. Defining a Numpy universal function gives you automatic broadcasting. It gives you for free the reduction methods, so the reduce method, the accumulate method. I don't know if they are very widely used, but they are useful. And traditionally, if you want to define a universal function that doesn't already exist in Numpy, you have to code it in C, which is very annoying. So actually, there's a way in Numpy of defining ufuncs in pure Python, but it produces very slow code. So what the vectorized decorator does is allow you to define your universal function in Python and have it compiled to a raw native function that will inherit that from all the nice behaviors of ufuncs. So there is another kind of universal function which is called generalized universal function, which is even more fancier. Because in that mode, your universal function isn't seeing only one element, but it can see an arbitrary number of dimensions. So it's quite advanced, but it has some applications. For example, if you want to write a moving average function, your moving average will actually have to get a view of the whole array for each element. So a moving average will have to be a generalized universal function. Numba also has its own decorator at GUVectorize to allow you to define generalized universal functions in Python. So here is an example. So we're defining a relative difference. So this is an arbitrary definition of a relative difference, I think. We have the absolute value of a difference, and we divide it by the sum of the absolute values. So you see in the definition that the vectorized function really operates on two elements. It doesn't know that there are arrays behind it. So we want to compare this speed to the speed that we obtain in straightforward Numpy code. And we, on a large array, we observe that we get, in this case, on my computer, a 3 times speed up. And why is that? Is that because when you write the Numpy array expression, Numpy will run in each operation on the whole array. And it will do that once at a time per operation. And so the memory accesses are not optimized at all. By contrast, if you call the vectorized relative difference function, then it will run the whole expression on each element. So it's much nicer to the CPU caches. So yeah, as written, vectorizing optimizes the memory cost on large arrays. So here is another example of using the JIT decorator, a bit more of a real-world example, I think. So it's something called Ising models. So I don't know exactly what they are used for. They are used by physicians for, I don't know exactly, but yeah. It's, the example was written by one of my colleagues. So an Ising model is basically a dynamic model where you start from so the state is a 2D grid of points. You start, for example, from a random state. And on each iteration, you evolve each element based on each of its neighbors. And there's also a random perturbation which adds a bit of sort to the mix. So this image was generated with Numpy or Numba. So how does the code look like? So there's one function, which is the inner function, which runs one update on an element of the array. So it takes the array, it takes the indices of the element of the array, and it computes a modification on the element based on its neighbors and based on a random variation. And there's an outer function which runs on the whole array and just calls the inner function on each element. And so what we did to compile them with Numba, we just added the number.jit decorators. So what does it do in terms of performance? Well, compared to the PyPython version, the Numba version is 130 times faster, so it's not bad. It's not exactly the raw speed of C or Fortran. Someone wrote a Fortran version, and the Fortran version ended up twice faster than the Numba version. So Numba is really making the code much faster than PyPython, but there are still some optimizations that we can improve, I think. And we actually know why it's not as fast as Fortran on this case. So so now CUDA support. So I mentioned you can run some code on the GPU using Numba. So there's a CUDA.JIT decorator, which works kind of almost like the JIT decorator. So it doesn't try to hide the CUDA programming model. I don't know how much you know of the CUDA programming model, but it's quite different from the normal sequential programming model that you have to use on CPU. So the CUDA programming model exposes a model where you have your function is actually executed on a large number of threads at once. And those threads are organized in a topology, a several level topology. So the first level is blocks of threads, and the second level is grids of blocks. And each of this level can be either 1 dimension, 2 dimension, or 3 dimension. And there's another distinction that is important in the CUDA model, is that there are two kinds of functions. The main functions are kernel functions, this is their name. This is functions that are called from the CPU and executed on the GPU. And there are device functions, which are called from the GPU and executed on the GPU. So device functions are really subroutines. And Numba allows you to write both of those kind of functions. So there's a limited array of features available, as I mentioned at the start. The problem is that some of our features require some C helpers. There are other reasons. For example, our random generator is a Mersenne twister, and this has a very large state which doesn't really work well on a GPU. So also the programmer needs to make use of CUDA knowledge, because we don't hide the fact that there are grids of threads and so on. And the programmer, if they want to have optimal performance, needs to take the hardware compatibilities into account. So a quick example to show how it looks like. So you have a CUDA.JIT decorator. Inside your function, so this is a function that computes the cosine of an array. So you have the first argument is the input array, second argument is the output array. But the function in each thread which only operate on one element. So you have to get the element index. This is what the CUDA.grid helper does. And then you compute the cosine and you put it in the output array. So if you do a small benchmark, you see that you can be quite faster than a CPU on this. Oh, and at this point, you see the thread config there. The thread config is how you configure the thread topology of your kernel function. So here we see that we have a manual definition of the thread topology, and the numbers have to be tweaked based on your GPU model to know to try to obtain the maximum performance. So how do you install Numba? We recommend that you use Conda. Conda is the package manager developed by Continuum Analytics. It's open source, and it's available in two forms. You can either download the whole distribution, which is named Anaconda, which comes with all the binary packages, or there is something called Miniconda, which only installs the Conda package manager itself, and then when you install something, it downloads it from the internet. So if you have Conda on your machine, you just write Conda install Numba, and it works on Linux, Windows, OS X. Otherwise, the manual way is you install LLVM 3.5 yourself, you compile it, which requires a recent C++ compiler. You compile LLVM Lite, which is our own wrapper around LLVM, and then you install Numba from source. So, the end. So we have, of course, So this is our website, numba.pydata.org. There's documentation on the website. The code and issue tracker are at GitHub, so we welcome any bug reports and pull requests. There is a Numba users mailing list, so it's hosted at Google Groups. So I haven't put the URL because it's huge, but you can find it on the documentation site. And at the end, I must mention that Numba is commercially supported. So if you have any specific needs, we sell some consulting. You can try to ask us for enhancements or try to fund support for new architectures. And at the end, we have also a specific product called Numba Pro, which is a proprietary extension to Numba. And it gives you access to some specific CUDA libraries, for example, optimized linear algebra for CUDA. And I think it also gives you the possibility to, it gives you high-level facilities to write parallel code, multi-threaded code, both on the GPU and the CPU. Okay, so any questions?